then this can result in what we know in statistics as a bias or biased estimate. So if we don't take into account other relevant variables such as education, background, and so on and so forth, then the effect of age is likely to be biased. The estimate of the effect of age is likely to be biased. Therefore, it's important in the regression analysis to use all relevant variables. And as I told you, the idea of the regression analysis is to determine the contribution of each of these factors in the variation of our variable of interest. So this variable of interest is typically called dependent variable and denoted as y. This is a convention. So y is the variable that is subject to impact of several factors. These factors are denoted as x, and they are also known as explanatory variables because they explain y or regresses. By the way, y is sometimes denoted as regression, so something which is being dependent on regressors. Sometimes some people use, instead of explanatory variables, they denote x as independent variables. But I prefer to use explanatory variables because it's a little bit less, it's a little bit more neutral, less involved. So these dependent variables, they're not really always independent. So let's say y is our dependent variable and x's are explanatory variables or regressors. Okay, so in this course we will consider linear regression analysis, although in the end we will consider a few cases of nonlinear relationships. But in general, we are talking about linear regression analysis as regression model which is linear in parameters. So the dependent variable is linearly related to regressors. So let's start considering, for simplicity, the regression, the specific case of regression, namely the linear regression with a single regressor. So it can be expressed as this linear model. So if we do not look at the last term, then we'll see the typical linear model that we know from the school, from the high school. So here we have dependent variable. Here we have explanatory variable x. Beta 0 and beta 1 are some constants. So typically it is assumed that there are some constants that relate x to y, but these constants are unknown and they are not observed. So we want to estimate beta 0 and beta 1. And there's also some epsilon, which is defined as random error. And I'll say a few words about random error in a second. Notice also that we have some indices, yi, xi, epsilon I. These are the indices denoting each observation. So I think we've seen already them in the previous analysis. So typically, if we have a sample, then each member of the sample, each observation gets its index, and that's this small I here. Okay, so for example, we have 200 persons with the income of each of these persons, and if we have the sample, then each person gets his or her index in this sample, which is a unique index. Okay, so typically we denote the relationship between, for example, two variables as a scatter diagram. We've seen it already last time when we considered regression correlation analysis. So here we have explanatory variable, and here we have a dependent variable, and this is a cloud of points that denote the relationship between them. You see that the slope is positive in this case, and the points are pretty much clustered around the straight line that I can draw here. Okay, so this strong positive relationship between x and y. The x increases, the y increases too. Okay, and the idea of regression is to draw a straight line through this cloud in some optimal way. What kind of optimal way it is, we will consider a bit later. But this you know probably from Excel and some other programs that draw this regression line for you automatically without you knowing what's going on behind these estimations. Okay? So the idea of regression analysis is, to put it simply, is to draw the straight line in the best possible way through the cloud of observations. In this case, it's easy to plot it because it's regression with a single explanatory variable, but it's more complicated in the case when we have more than one explanatory variables, because in that case it's already plane or surface or some more complicated object. But it's easy to display it for this one regressor case. So recall we have a linear model. So in this case, this is really a function of a straight line. Here we don't have any error because it's the straight line. It's not the points around this straight line that differ from it because of the random variation, random errors. So beta 0 is our intercept, a constant, and it's basically, it can be basically defined as the level of yi of dependent variable when our explanatory variable is equal to 0. So here x is equal to 0, and that's the intercept or constant, okay, beta 0. Now the slope of this straight line, I hope you can see my mouse, my cursor. Can you see? I mean, you cannot see my mouse, but you can see the cursor. Can you see it? Okay, so the slope of this straight line is beta 1, and it's therefore it's also called slope, and it shows both direction of the relationship and its strength. For example, the higher the slope, the stronger is the relationship. If the curve is parallel to, if the line is parallel to the horizontal axis, then there's no relationship at all. And the sign of beta measures in which way the relation goes, whether it's positive or negative. Now let's look at an example of some regression. Here I used some real data taken from a survey of households and persons in Germany. So here I used, as you can see here, almost 4,000 observations. And I took as a dependent variable income level, the net income of persons, and I regressed it on the age of these persons. And you see here we have both constant and slope here. So the constant is very big because it's the income of the person with age 0. Well, it doesn't make too much sense, but in the linear model context, it has some sense. So if there's no factor of age, then the income will be equal to 1,100 euros. Now this coefficient here measures the impact of age on the income. So the income is measured in euros, the age is measured in years. So you see that for each additional year, the income increases by around 30 euros, okay? Which has to do with, for example, experience of people, of education. But of course, the relationship is not that linear. We could think about introducing some nonlinear terms, but let's for the moment forget about this. Now, what happens here? So the numbers here are a little bit too big. It's not a problem, but it's not very nice. So we may think about dividing this income variable by 1000. So in this case, what happens with the constant? It's the same thing, but divided by 1000. What happens to the slope? It's also the same thing, but it's divided by 1000. So 1 year in both regressions, 1 year more means 30 euros of income more. Okay, so very, very easy. Now there are some other pieces of information, these stars here and the numbers in parentheses and also R squared and adjusted R squared. I will talk about this later. Okay, so let's first discuss a bit the random error that we included that we typically include in a linear regression model. So it's the part of variation that cannot be explained by X, by our regression model. And there are many sources of error in regression. Well, first, unpredictable randomness of human behavior. So humans behave not like automates. They can change their behavior and behave differently in exactly the same conditions. I told you that we need to, so the second factor is the large number of missing variables. I told you that it's better to have all relevant variables in your model, otherwise the results will be biased. But of course, it's impossible to take into account all variables. And there are some relevant variables, some irrelevant ones, and the number of irrelevant variables can be very big. So we cannot really take them into account because we don't have information on them. We don't know what kind of variables these are. So necessarily we will miss some information, and this will cause the random error in our regression. And the last factor that leads to occurrence of random error is measurement errors. So for example, when filling in the questionnaires, we can make typos. For example, instead of 1000, we can write 10,000. There can be rounding problems. So if we round up our age, for example, so we are, I don't know, 22 and a half years, but we never write 22, we write 23 or 20. We never write 22 and a half, we typically write 23 or 20 years. The income can be also rounded and other variables too. And there are some approximations. So together, these factors lead to appearance of a random error epsilon I in our regression. So the part of the regression that cannot be explained by the model. Graphically, we can show these errors like follows. So each point is y, I, meaning observed values of x and y. Okay, so we observe x and y, and these points are what we observe. So if we did a survey and then we plotted the scatter diagram, then we will see these points here. Now the green line, regression line here is not observed, it's estimated. So it doesn't exist in reality, it's a product of our estimation. We denote typically the estimated or fitted values as y hat. And now the difference between this y hat, so y hat is typically beta 0 hat, estimated beta 0, plus beta 1 hat, estimated beta 1 times xi. Okay, and now if we draw this straight line here, then we will never touch all these points. So some of the points, they will lie really on this line, like this point, this one, this one, this, and especially this one, it's exactly on the line, but most of other points will be outside of the line. And the difference between this line and the actually observed points is the regression error. So this height here, this dashed line measures the regression error. And you see that some errors are very small. Here the error is equal to 0. Some errors are bigger. But the idea is to minimize somehow the errors, the deviations from the fitted y hat. Okay. So how to draw this line, how to estimate the intercept and the slope in the best possible way? Well, there are different methods how to do this. So the most popular and the one that we will consider here is called ordinary least squares. Please put something like yes or cross if you know this method, and minus or no if you don't know it. So okay, some of you know it, some do not know. So for the abbreviation for ordinary least squares is OLS, and we'll see, and you will see it also pretty frequently in the future, in the nearest future already. Another method is maximum likelihood method, or maximum likelihood estimation, sometimes denoted as ML or as MLE. In this course, we'll not talk about this anymore, but later you may face this technique. There's also a general method of moments. It's very likely that you will never meet it in your life. And there's a Bayesian method. Probably some of you heard about it. It's often used in, for example, in machine learning. But actually, OLS is also used in machine learning. So typically, so actually, all these methods can be part of machine learning. But we'll concentrate here on the ordinary least squares, on the OLS technique. So the idea of the OLS is to minimize the sum of squares of linear regression errors. So remember these deviations from the straight line. So we square them, and we compute the sum of these squared errors, and we want to minimize the sum of squared errors. So what we have here are the observed values of y, and these are the fitted values of y. So yi minus y hat is basically the regression error. It's squared and summed across all the observations from the first to the last one. And we want to minimize this sum given, and from this minimization problem, we can derive expressions for beta 0 and beta 1. Okay? So, as I told you, the estimations of beta 0 and beta 1 are denoted by hat. These are predicted or fitted values of y, and the residuals are the difference between the observed values and fitted values. Okay? So how do we do? So here we have a minimization problem. We have two parameters with respect to which we can minimize this expression. And you may remember from the course of mathematics, in order to find the optimum, we have to find partial derivatives of this function. So we have function q, which is equal to sum of the squared errors, and we find partial derivatives with respect to beta 0 and with respect to beta 1. And then these are the first order conditions, and as you probably remember, the first order conditions must be equal to 0 in order to find the optimum. So I won't go into much details. In the end, what you get is the expression for the intercept. It's the mean of y minus mean of x times the estimate of beta 1. Now the question is, how do we obtain this estimate for beta 1 here? And that's the expression here. So basically, it's very similar to correlation coefficient. The only thing is that here, instead of standard deviation of x times standard deviation of y, we only have variance of x. Okay, but this upper part is nothing else than covariance between x and y. And so it has correct sign. So if x and y are negatively correlated, then the coefficient will be negative. And its size it's not like correlation, which is unitless. It varies between -1 and 1. In case of slope and also intercept, by the way, there's no such limitation. It doesn't vary between -1 and 1. It can take any value. And it's as we've seen, when we divide, for example, the dependent variable by 1000, then also the coefficient changes by 1000. If we multiply it by 10, then the coefficient will go up by 10. So it's not like correlation where we don't see any transformations, linear transformations of y and x. Here, they are immediately reflected in the value of beta 1. And then we can also compute the error variance, sigma squared hat. This is the sample estimate. Therefore, n minus 2, n is number of observations in the sample. And here we have the deviations from observed values of y and fitted values of y. So this y0 hat plus, not y, beta 0 hat plus beta 1 hat times xi. These are the fitted values of y. And of course, we are interested in the estimates that have the lowest variance of errors, the lowest unexplained part of the variation. And this leads us to the measure of the goodness of fit of the model. So we are interested in those models that have the best explanatory power, the highest explanatory power, meaning that the unexplained part is smallest as possible. So typically, we will always have some errors, but if we compare two models, the model that has smaller errors, a smaller sum of errors, is the better model because it has smaller unexplained part. Okay. So how to measure the goodness of fit of model, the precision of model? Well, for this, we use the measure of R squared. Sometimes it's also known as a coefficient of determination. And it's a measure that varies between 0 and 1, where 0 being very low explanatory power or non-explanatory power, and 1 being the perfect explanatory power. When R squared is equal to 1, it means that there's no unexplained part, there's no error. By the way, why it's denoted as R squared, the reason is that it happens that if we have a linear model with singular regression, then this R squared is equal to square of the correlation coefficient between x and y. Therefore, here we have R squared. Okay, an interesting property. Now, how can we interpret R squared or coefficient of determination? So it's the fraction of the variance, sample variance of y that is explained by our explanatory variable x. Okay, so here we have the explained sum of squares. Here we have total sum of squares. And well, the explained sum of squares is defined as the kind of variance of fitted values. And this is the total variance of y. So the bigger this term, the bigger R squared, and the better our model explains the data. Okay, this I already told you that it's a positive value. Well, you will see that there's adjusted measure of R squared that it can be negative, but R squared cannot be negative. It can only be between 0 and 1. Now let's look at an example. So we continue with the same regression of net income on age. So here we have R squared. We won't talk about adjusted R squared for the moment. We will talk about this during the next lecture. But here you see that the number is the same. Well, because we only divided the income by 1000, so it shouldn't affect the explanatory power of the regression. And what do you think about this regression? Does it explain the data well or badly? Looking at the R squared. Is this regression, well, regardless of which regression we look at, this one or another one, okay, not good. So the, in, yeah, or in other words, bad. Why it's bad? Because this model explains only 6% of the total variation, and it's very little. So ideally, we would like to have a model that explains at least 90% of the total variation. So 10% being some additional errors that can be explained, for example, by missing information. But just 6% is too little. Okay, so typically we would prefer to look at a model where R squared is much bigger. So the age explains to some extent the income, but it's not the only factor that explains income, and it's not the most important one. Okay. Now let's talk about testing, because here we can also apply the same kind of tests, the compute confidence intervals and determine statistical significance, as we do previously when we talked about, for example, such parameters as mean. So exactly as the mean, beta 0 and beta 1 are estimates of some unknown constants, beta 0 and beta 1. So we suppose in the OLS methodology, or in the maximum likelihood estimation, we assume that there are some unobserved true values of beta 0 and beta 1 that we will never observe, but we can estimate them. We can find some values that are close to this unobserved beta 0 and beta 1. However, we would like to know how far we are from these true values, or how closely we are to them. So for this purpose, we compute confidence intervals, the intervals where the true values will be located with certain, possibly high probability. Okay, so we estimate, so we know that beta 0 and beta 1 are some functions of x and y. X and y are random variables, therefore beta 0 and beta 1, the estimates of beta 0 and beta 1 are random variables. Beta 0 and beta 1 are not variables at all, they are constants. But their estimates are random variables because they are functions of random variables. And the probability that we need to compute confidence intervals depends on the probability distribution of x and y. So in big samples, so when n is large, we can say that both coefficient estimates are normally distributed. So each of them has its mean and its standard deviation, or in this case, variance, sigma squared beta 0. Don't confuse it with the standard deviation of variance or variance of errors, which is sometimes denoted as sigma epsilon. So these are two random variables, and of course they have if they are normally distributed, then they have mean and variance. So if we subtract the true value that we don't observe and the standard deviation that we don't observe either, then we get a standard normal distribution with mean 0 and variance 1. Okay, this we did already when we constructed confidence intervals for means. Now, since sigma beta 0 and sigma beta 1 are not known, are not observed, we have to estimate them. And therefore, we replace these unobserved variances by their estimates. So also with hat. So hat allows us to distinguish graphically the estimates from the true values. And as we know, if we divide some normally distributed variable here by some chi-square distributed variable, because the variance is follows chi-square distribution, then the resulting variable here will follow the normal distribution, the t distribution, the student distribution, with n minus 2 degrees of freedom. Why n minus 2? Because we have two regressors in our model. We have a constant and we have explanatory variable. Okay, typically constant is not called explanatory variable because it doesn't really explain anything. So we have two variables in our model, constant and explanatory variable. So we have n minus 2 degrees of freedom here. So each of these coefficients follows, or transformation of these coefficients follow t distribution with n minus 2 degrees of freedom. So how to construct the confidence intervals? So in this case, we construct, for example, these intervals using some null hypothesis that for example, we concentrate only on coefficient beta 1 because it's the one coefficient that is of utmost interest. It's not very interesting whether the constant is different from 0 or not. But whether beta 1 is different from 0 or not is important, because if it's statistically insignificantly different from 0, then beta 1 has no impact on y, or I has no impact on y. So we are interested in the null hypothesis where the beta 1 is equal to 0. But in a more general case, we can consider other cases when the true parameter can be different from 0. It can take some value b1, which is positive or negative, for example. So in this case, the null hypothesis will be that beta 1 is equal to b1. In a specific case, it can be 0, but not necessarily. And the alternative hypothesis will be that beta 1 is not equal to b1. Okay? And now we can say with assign certain significance level, 1 minus alpha, and construct the confidence interval. So in this confidence interval, so this is here I should have put beta 1 instead of k, but I did it for more general case. For example, if we have more than 2 explanatory variables, or if we still want to test the significance of beta 0 coefficient. So this is the lower boundary of our confidence interval, and this is the upper boundary. So within this confidence interval, the true value will be located with a certain probability, with probability equal to 1 minus alpha. Okay? And here we have the estimate of beta. Here we have a quantile from t distribution, and we multiply this quantile by the standard deviation of beta. Now let's consider a simple example to understand it better. So assume that we have some dependent variable, which is the volume of sales, and we have explanatory variable, which is advertising costs. So we expend some money on advertisements, and we expect that it will lead to some increase in the volume of sales of our product. So assume we had some, I don't know, n days or n advertising campaigns, or n cities where we did these campaigns, and we have two regressors, a constant and advertising costs. So k is equal to 2, and we estimated linear regression where beta 1, estimate of beta 1 is equal to 12. And its standard error is equal to 5. Now tell me, please, what's the effect of advertising costs on sales? Is it in which direction it goes? Yeah, exactly. So the coefficient is positive, beta 1. So the more we invest in advertising, the more sales we get. But the question is still, there's another question that we would like to solve is whether this effect is, so what is the confidence interval where the true value is located with a certain probability? So whether it's really 12 or maybe 10 or 5, and what is the whether this coefficient is statistically significant. We know that these are random numbers, so in some sample it can be 12, in another sample it can be 3. So we would like to be more confident about this value of the estimated coefficient. So first, what we do, we compute the confidence interval. So how do we do this? So we need to set the confidence level. So we say alpha is equal to 10%. So we have 102 and 2 observations minus k, which is equal to 2. So the number of degrees of freedom is equal to 100. So we go in our table. We have a two-sided interval because we consider all the alternatives when beta 1 can be bigger than 12 or smaller than 12. And therefore, we have to look here not at 90%, but at 95%, okay? So the intersection between 100 and 0.95 is 166. And this is our t-statistic here that we place in our formula. So we put it here. And we multiply it by the standard deviation of beta. So typically, we get standard error of beta in our regression output. So here, if you look at the numbers in parentheses, these are our standard, not our standard errors, they are standard errors of the corresponding coefficients. So for example, 0.02 is the standard error of the coefficient of h, okay? So we take this, in this particular case, the standard error of beta 1 is equal to 5. So we plug it into regression, we multiply, so here we have 12, the estimate of beta 1, minus t-statistic, corresponding to 100 degrees of freedom and the probability of 0.95.
Hey everyone, boy do we have a crazy video to go through today. The full self-driving beta seems to have grown a pair with the last software update, and you're going to see some crazy aggressive San Francisco human-style maneuvers that are definitely brand new behaviors that I have never seen before. And while on paper this is only a small dot update of version 11, I think you're going to agree that it is quite a major one, only disguised as a minor one. And while this 3.5-hour drive was definitely far from perfect, you're going to see what it's like when really pushed over the limits and also what it's really capable of. Now, a little disclaimer before we begin, full self-driving is still in beta, and I am responsible for the vehicle at all times during these drives. There are quite a few times where you're going to see some behavior I probably should have intervened for, but I'm purposely giving the beta as long of a leash as I possibly can. For science, of course. 84 countries and all 50 US states.
One-sided problem, for example, smaller than
here trying to get a better view to see if there's any type of left-hand turn that it can make, but obviously there is not. Then something interesting happens. A Model 3 approaches from our right, and it seems to understand that it can go that way. And I'm going to transition back inside the car here for a second just to show you that the navigation path has not updated, meaning it seems to be figuring out how to get out of here by using vision alone and abandoning its navigation route, which I think is very impressive. I've actually tried this same thing in the past, but previously was unsuccessful. So this version seems to be able to abandon its navigation route and follow vision a little bit better than previous versions. And approaching the last stop sign, it was listed in the release notes that the visualizations have been improved, but no mention of what exactly was improved, so it's kind of up to us to figure it out. I don't necessarily see anything brand new on them, like updated car models or anything like that, but what I do notice is that it seems to be able to see and visualize traffic a lot further out, and also the roads and boundaries it's drawing are extremely steady. It used to be that when areas of the road were obstructed, the visualizations would kind of become unsteady, but they seem extremely solid now. It's kind of wild to me to compare the visualizations we have now to the original 3D boxes we got with really early versions of the beta. Definitely looking more and more polished with every single update. Waiting our turn at the stop sign, and you can see autopilot.
Its lower boundary is higher than 0, meaning
the driver in front of us takes the opportunity, and while the oncoming car was obstructed, the beta started detecting it as a parked car. Honestly, probably a pretty well-deserved honk there. I did submit a snapshot to send this data back to the autopilot team for them to review. You could definitely argue that I should have disengaged in that moment, but honestly, I see moves like that happen in San Francisco all the time and didn't feel that there was a safety issue, but definitely not what the car should have done. The good news in all of this is that it didn't panic and stop in the middle of the road when it saw the oncoming car approaching. It continued its original plan maneuver and got out of the intersection, which is much better than previous versions would have done, but still not the right thing to do. I do have the car in the assertive autopilot setting, but man, this was assertive and a half. It was the most assertive I've ever seen, until later in the drive at least. What happens next here is truly remarkable, but it has nothing to do with autopilot. The gentleman in the back seat of the car to the left seems to recognize me and rolls down his window to say what's up, but not only that, the car to our right also does the same thing, and he says he watches my YouTube channel. And ladies and gentlemen, for that brief moment of time, I was literally surrounded by fans. I think this means I've finally made it. All joking aside.
Sometimes in the regression output you will find the confidence interval for each parameter. But more frequently you will see the stars, and the stars, they denote the significance level. Now, how to determine this significance level? So in this case, we do not look at the confidence interval. We just want to test hypothesis whether beta 1 is equal to some b1, to some constant, which can be 0 or some other value, against the alternative hypothesis that it's not equal to this beta 1. So what we do in this case, we calculate, we estimate the standard error of beta 1, but we've seen that we get it already in the regression output. Then we calculate the test statistic. Don't confuse it with the value taken from the table.
Bloated, though? That's what's called the bloat phase. By the end of the bloat phase, we get into the next phase, and that's when it gets really stinky, and I was really worried. That's what's called active decomposition. And so basically, Saturday and Sunday, and just a teeny bit of Monday, the maggots ate from the tail all the way to the head.
Here we can either use statistical software or the distribution table. For example, so here what we did,
Today's Sunday, it's day 5. Oh, we're stinky. Look at this.
When we compute confidence intervals. When computing statistical significance, we look at the values here. For example,
but it's also fascinating. I think I can 100,000 blowfly larvae, beetles, which have been going around.
Hat minus b1 divided by standard error of beta 1 is equal to 2.08. Okay, the closest value is here. corresponds to the probability of 98, which means that with probability of 2%, the true value will be different from beta, from beta. Now let's look at our algorithm here. So we computed this test statistic. We looked upon the distribution table here. We found the corresponding probability in the table, and this will give us this will result in the p-value, in the probability of observing this value, given that it follows t distribution with n minus 2 degrees of freedom. And we will reject this, for example, if we set significance level of 5%, we will reject the null hypothesis if the p-value is less than 0.05, or if the test statistic computed here, absolute value of test statistic, is greater than 1.96. 1.96. 1.96 is, it must be here actually. Wait a second. I think it's an error. So it should be if it's 5%. Oh, well, it's in more general case when n is very big. So when n is very big, then this value tends to 1.96. So here we have relatively small samples, 100 and 150. But if, for example, n is bigger, then this value tends to, for example, when n is equal to 100, then this value tends to 1.96. Therefore, I used here this value of 9.26. Well, let's consider an example. So in this, for example, in this case, we have the estimate of beta 1, we have its standard error, and we can test a hypothesis, the null hypothesis, that this value is equal to 0. It's very small, so it would be logical to suppose that it's not different from 0. So if it's not different from 0, then it means that h has no impact on the income. Okay, so what we do, we compute the test statistic. We subtract from 0.030, which is, of course, the same number, 0.03, and we divide it by the standard error of this coefficient. So it's 0.002. So we have to divide 0.03 minus 0 by 0.2. Can you give me the number? What will be the result of this? Exercise. So, okay, Gleb, according to Gleb's estimations, it's 15. So what we can do, we can either compare it to take the absolute value. Well, in this case, it's the same because it's not negative. The coefficient is not negative. If the coefficient were negative, then we would take it's with minus sign. So if, for example, if the coefficient, the test statistic would be minus 14, then we'll have to take the absolute value of minus 14, which is equal to 14. Okay, so if the value is positive, we work with this value. If it's negative, we take the absolute value of it. So here the coefficient is positive, so the value is, the test statistic here is positive too. So we either have to go into the table here, and we see, well, we don't see this value, but we see that already with 3 we have the probability of 0.999. So the p-value is actually the probability 1 minus probability here. So the p-value here will be something like 0.0 or less than, much less than 0.01. Okay, so unfortunately I don't have here the full table, but if in the statistical software you plug the 15 value and you want to find the p-value, the probability that values larger than 15 can be observed, you will get something which is some very, very low probability, some very low p-value. Alternatively, what you can do, you can say, okay, I'm testing the hypothesis with alpha equal to 5%. In this case, the test statistic is equal to 0.976, and it's much smaller than 15. So I can reject the null hypothesis because our test statistic is much bigger than the critical value. And I say that in this case, our null hypothesis was that beta 1 is equal to 0. And the alternative hypothesis was that beta 1 is not equal to 0. So if we obtain a very big t statistic, 15 in this case, then we can reject the null hypothesis. So we assume that the coefficient is statistically different from 0. And we accept the alternative hypothesis H1. So there are two ways to do this. Either we take from the table some critical value corresponding to 5%, or to 10%, or to 1%, and we plug the test statistic into the distribution and obtain the corresponding p-value. The larger the coefficient here, the smaller will be p-value. Small p-value means that we reject the null hypothesis. Big p-value, meaning bigger than alpha, for example, than 5% or 10%, means that we cannot reject the null hypothesis, so we accept the null hypothesis and we don't accept the alternative hypothesis. Is it clear, or it's a bit complicated? I assume that you will have these exercises during this today's seminar. So you will train yourself on how to use it. But I want you to know that p-value measures the probability that test statistic is observed given t distribution with n-2 degrees of freedom. And if t is very big, then the probability of observing such values is very small. So p-value is very small. And if p value is small, then null hypothesis is rejected. So whether p-value is small depends on how do you set alpha. So you have to compare the p-value with alpha. If alpha is 0.5, then small p-value is everything which is smaller than 0.05. If your alpha is equal to 0.01, then small p is everything which is smaller than 0.01. And if p is small, then you reject the null hypothesis. So the null hypothesis can be that the coefficient is equal to 0. So by rejecting it, we assume that the coefficient is statistically significant different from 0, like here. So here you see below, there's a note saying that if there's 1 star, then the p-value is smaller than 10%, 2 stars, it's smaller than 5%, 3 stars, it's smaller than 1%. So in this case, it's smaller than, the p-value is smaller than 1%, meaning that with 1% probability, we can reject the null hypothesis that this coefficient is equal to 0. But again, we can also test other hypotheses. For example, beta 1 b1 is equal to 0.05. In this case, we have to subtract 0.03 from 0.03. We have to subtract 0.05 and divide it by 0.02. Can you please compute this number? So in this case, we test the hypothesis that the coefficient is equal to 0.05. So again, we have, thank you, Anna, we have minus 10. So we have to take the absolute value of minus 10, which is equal to 10. And we either plug it into our regression, or we compare it with, for example, if our significance level is 5%, we compare it to 0.976. For example, if we have 152 observations, and we see that 10 is much bigger than this value here, so the p-value must be very small, and we can reject the null hypothesis at 5%, but also probably at 1% level. So the coefficient is not equal to 0.05. So here we can test different hypotheses, which is important. Okay, do you have any questions? Because it's a very important topic. So typically, what we look in the in the regression output is the sign of the coefficient. So here it's positive, so the influence is positive. The size of the coefficient here 0.03 shows us how much the explanatory variable age contributes to the dependent variable y, or in this case income. And the third thing that we have to look at is the significance of these coefficients. So typically we get automatically these stars. So the more stars, the better. It's like with hotels or cognacs. So if we have here 3 stars, it means that this coefficient is statistically significantly different from 0. So age indeed affects income. Okay, so we have sign, size, and significance. And another thing we have to look at is the size of R squared. So this coefficient is okay, but the R squared is very small, so we need either to find another coefficient, or maybe not coefficient, other variable, or maybe some additional variables. So we'll have multiple regression with multiple explanatory variables. Okay, so if it's clear, then we have still 7 minutes, and we'll talk about the properties of the OLS estimates. So the OLS estimates have some nice properties. They are unbiased. So there's no systematic deviation from the true value. So the estimated values will be always different from the true value, but there won't be a systematic difference. So if we take many samples and compute estimate the betas for each of them, and look at the distribution of these betas, then the mean of this distribution will be close to beta. In other words, the mathematical expectation of estimated beta is equal to the true beta. Okay, and of course we need an estimate that is not systematically different from beta. Now, the second property is the efficiency. So if we have OLS estimate and we have some other estimate, then the variance or standard error of this beta estimated using OLS will be always smaller than the variance of or standard error of the estimate of beta obtained using other estimator. Okay, another nice property, because the smaller is the standard error of the parameter estimate, the more secure, the more precise we are about, the more confident we are about the true value of beta, and the narrower will be the confidence interval. And the last property, nice property of OLS, is its consistency. So if the sample is sufficiently large, the uncertainty about the value of beta 1 will be smaller. So the bigger sample we get, the smaller will be the variance or standard error, the variance of beta or standard error of beta. Okay. Now, in order for these properties to hold, we need that our data satisfies certain conditions, and this we call OLS assumptions. So we make some assumptions about our data. So the first assumption is simple. It means that the mean of random error is equal to 0. It's pretty easy to obtain it. We need to include in our regression a constant. So we're not obliged to have a constant in our regression. But if we have it in the regression, then the mean of the random error will be equal to 0. It will be guaranteed. So it's easy. Now the second property is more complicated because it requires that the variance of random error is the same for all observations. It's known as homoscedasticity, and the opposite of it is non-heteroscedasticity. So here, for example, we have the so-called identically and independently distributed errors. So the errors that satisfy the assumptions of OLS, and these are heteroscedastic errors. So here you see that the mean is equal to 0, and the variance is constant. So if we compute the variance for this subsample or for this subsample, it will be more or less the same. By contrast, here you see that the variance is very small, while here it's very big. So we have different variance here and another variance here. So the homoscedasticity condition is violated, and we have heteroscedasticity here. Why is it's important? Because well, I'll talk about this later. Why it's important to have homoscedastic errors. Now the errors, the values of epsilon of error they must be uncorrelated or independent for any index of I, j. So for any two observations, errors of any two observations must be uncorrelated, must be independent. We call it sometimes also autocorrelation or serial correlation of errors. So the assumption, OLS assumption, is that there's no autocorrelation or no serial correlation of errors. If this condition is violated, then the errors are autocorrelated or serially correlated. Now look at this picture here. Again, if we look at the first panel, you see that the sign changes from one observation to another very quickly, meaning that even visually we can observe that there's no relation between the previous epsilon and the next epsilon. Here you see that, for example, there are long periods when with positive values and big values of x, and then there are periods of negative and small values of not x, of epsilon. So there's certain relationship between, for example, the previous epsilon and this epsilon. Okay, so there's some autocorrelation, some serial correlation. This epsilon depends on the previous epsilon. Here too. So here there are erratic changes between observations, while here we see that there's certain relationship between the current epsilon and the previous epsilon, which implies that there's autocorrelation between them. And the fourth assumption is that random error must be normally distributed. So with mean 0, thanks to inclusion of a constant, and some non-zero standard deviation or variance. Okay, and if we consider the second, the third, and the fourth assumptions together, it means that our errors must be independent and identically normally distributed. For short, shortly we denote it as IID, normal, mean zero with sigma. And the last thing, yeah, indeed, you have to start with the test. So I wish you all success. I hope that the test can be open. And the rest of the lecture will be explained hopefully next time. Can you open the test? Okay. So good luck. Maybe we'll see each other sometime in the future. Next time, most probably, we'll have another teacher, and hopefully, he will bring you to the end of this voyage, known applied statistics or introduction into applied statistics. You're welcome. Bye.